Welcome to the third and final LIFE Waste2Coag webinar. I'm Eleonora Paisoni, Senior Consultant at IL Utilities, and I will give you a brief introduction to this webinar. The webinar series of LIFE Waste2Coag has a twofold objective: to raise awareness of the capabilities of the project targeting different stakeholders, and to improve the overall knowledge of the project with a view to responding to market needs. During the course of the project, 3 webinars were delivered on 3 different topics. In July 2023, the first webinar focused on brine generation and management. In May 2025, in the second webinar, we discussed about scrap metal production and valorization. And today, we're going to talk about the production and validation of the LIFE Waste2Coag coagulants, as the project is coming to an end. If you missed one of our webinars, you can find all the recordings on our website and our YouTube channel. As for today's webinar, we will start with a presentation by Dr. Felio Sempere from Global Omnium on LIFE Waste2Coag project context, ELS technology, and project methodology. Felio will then continue with a presentation on the results at the urban wastewater treatment plants in Gandia, in Spain, and Wulpen in Belgium, where the ELS technology was operated during the project. Following Felio's presentation, Laura Grima from AIDIMME will present the results of the operation of the ELS technology in the third case study of the project in the industrial wastewater treatment plant at project partner Joviar's facilities. After watching the webinar, we welcome your feedback on the ELS technology. You can find a Google form in the description of this video to leave your comments. And now, without further ado, I will hand over to Felio.
Felio Sempere Natcher, R&D engineer from Global Omnium, and in this presentation of this third webinar, I'm going to make the introduction of the project with outlining the project context, the technology, and the methodology. LIFE Waste2Coag project had a budget of around 1.5 million euro, co-financed by the European Commission, and it has 6 partners: AIDIMME, which is the Institute of Technology Development working for the metal sector in Spain; Joviar, an SME manufacturing of technical metal components in Spain; IL Utilities, a global independent technology and innovation consultancy from the United Kingdom; Aquafin, a wastewater utility company in Belgium; and Global Omnium, which we are the coordinators of the project, working in integrated water cycle. The problem we want to solve with this project is the treatment of brines with a production of around 142 million cubic meters per day produced only from desalination plants, from which 50% of their production is 50 kilometers away from saline water bodies, mainly in China, USA, and Spain. And these brines are discharged without treatment. We also have a scarcity of metal resources with a high price of these metals. And finally, we have also a high consumption of coagulants for urban and industrial wastewater treatment plants, which requires outsourcing them and with continuous price increments. Our solution is to produce alternative coagulants. We made this by electrolysis using metal wastes as electrodes and brines as electrolytes. In the anode of this sacrificial electrode, if we use steel, we are producing substitutes of iron salts, while if we use aluminum as anodes, what we are going to produce is alternative coagulants, substitutes of PAC. By using brines with their high conductivity, we decrease the energy consumptions to produce these alternative coagulants. The objectives of the project were technical: to design and construct an electrolytic pilot system, ELS, to produce coagulants valorizing these metal and brine wastes, validate these coagulants treating urban and industrial wastewaters, quantify the impacts by carrying out life cycle assessment and social life cycle assessment studies, and determine the economic potential by conducting a business plan. This project started some years ago, so there is a strong background. Work started with 100-liter reactor system that we can see in this picture, where we see an IBC to collect the brines, the electrolytic reactor, and the tank for the coagulants. In LIFE Waste2Coag, the system has been scaled up from 100 liters to 850-liter reactor with the same configuration. When we see a vessel for the brines, the electrolytic reactor, and also a vessel for the coagulants. The methodology implemented in the project required different phases, starting from a design and construction of the prototype, a second phase which dealt with the optimization of the prototype operation, in which we selected adequate metal and brines to be used in the system. We determined the optimum ELS residence time, the electrolytic residence time, the current density, and also the coagulant validation, toxicity, jar test, and once the prototype was optimized, we evaluated the production of the coagulants with different brines. This has been made with brines received at Gandia Urban Wastewater Treatment Plant located in Spain, using brines from 3 industrial companies. This wastewater treatment plant receives around 26 cubic meters of brines per week, with a conductivity ranging from 30 to 50 millisieverts per centimeter. Then brines from a company nearby Wulpen in Belgium, Wulpen Urban Wastewater Treatment Plants. These brines come from a drinking water facility really nearby the wastewater treatment plant, producing around 14,000 cubic meters of brines per week, which are discharged to the North Sea, but with a lower conductivity, 5 millisieverts per centimeter. And finally, industrial brines produced at Joviar facility, where they have an industrial wastewater treatment plant, were also used to produce the coagulants. These brines came from processed water that Joviar needed for their production process, producing around 1.5 cubic meters of brines per week, but with a very high conductivity of 180 millisieverts per centimeter. Finally, the methodology included the validation of the coagulants treating urban and industrial wastewater. In Gandia urban wastewater treatment plant, the coagulants were dosed in the biological reactor of a pilot unit with continuous treatment, mainly removing phosphorus. And in Joviar Industrial Wastewater Treatment Plant, which is a physicochemical system, the validation of the coagulants was with a batch treatment, discontinuous treatment. And in this plant, the waste-to-coag coagulants was an alternative treatment to the current coagulant based on lime. And the objective of this demonstration was to remove the metals that Joviar has in their waters. Firstly, talking about metal selection, there were quality requirements. Different types of metal wastes were identified. The final selection was based on a high purity in aluminium and iron, the low price, and suitable shape to facilitate the electrodes manufacturing. The aluminium electrode had a high concentration of aluminium and very low content of alloying elements, and the iron electrodes were not stainless steel nor galvanic and had also a high purity of iron with below 2% of carbon and very low content of chromium, nickel, and zinc. The brine selection for urban wastewater treatment plant, as mentioned before, had different sources from reverse osmosis and ion exchange, from manufacturing of industrial and household cleaning products, and from the production of drinking water in the case of Wulpen, the test done at Aquafin. In this table, you can see a characterization of the different brines used to produce the coagulants. The energy efficiency costs were determined by the were decreased by using high conductivity brines, which was also a requirement for the system. And the quality was also important to have the lowest presence of metals and other contaminants. In the case of Joviar, the industrial wastewater treatment plant, Joviar has a demineralization equipment which has different stages and separation of streams from resins regenerations carried out once per month. In this table, you can see the different streams and stages with different volume produced. And in this case, not all the stages of the brines were appropriate to be used in the electrolytic system to produce the alternative coagulant. So a run of 65 to 70% of the total volumes of brines, which is a high percentage, was valorized to produce the coagulants. This mixture of brines has the characterization shown in the right table. And thank you for your attention. In this presentation, I'm going to show the results of the project at urban application of the ELS at urban wastewater treatment plants in Gandia and Wulpen. First, an overview of the companies operating these wastewater treatment plants. Aquafin is fully owned by the Flemish region, operating key wastewater infrastructures in Flanders. Aquafin operates 332 wastewater treatment plants, more than 2,000 pumping stations, with more than 7,000 kilometers of pipes. Their treatment results show more than 99% of compliance with all the standards of their wastewater treatment plants, with a financial turnover for the Flemish region of almost 600 millions of euros. Global Omnium, operating Gandia Wastewater Treatment Plant, is a business group of the integral water cycle with headquarters in Valencia, Spain, and in the last 5 years we have executed more than 30 projects with more than 5.5 millions of euros executed. It has more than 135 years of experience, international presence in Latin America, USA, Africa, and Middle East, and it operates drinking water treatment plants and also wastewater treatment plants. So we have brine generation and coagulant consumption in the same company as operating in integral water cycle with more than 2,500 workers in the group. Gandia Wastewater Treatment Plant is located in Spain near the Serpis River. It doesn't have a phosphorus limit in discharge with discharging to the sea, and it treats around 40,000 cubic meters per day of wastewater. Wulpen in Belgium has a 2 milligrams phosphorus per liter limit discharge, treating around 16,500 cubic meters per day of wastewater. The results of the coagulant production. Firstly, we used iron electrodes, but we experienced a faster deterioration than expected due to the type of brines treated in the process. We experienced electron delamination and breakage, which increased the current tension and the energy consumption in the system, implying also an increase in personal maintenance hours. As you can see in this picture, where the deterioration of the electrodes is shown. On the other hand, when using aluminum electrodes, there was a lower delamination and breakage, so a higher lifetime than when using iron electrodes. So the aluminum electrodes were the ones selected to produce the alternative coagulants, hence producing aluminum-based coagulants substitutes of PAC. In this image, we can see the process. New anodes were introduced in the system. The electrolytic cycles were carried out. Once they were spent, the removal of the anodes and cathodes for the reactor was done. Cleaning of the cathode had to also be done. And then the installation of the new anodes and the clean cathodes in the system to continue producing more coagulants. About the coagulant production, in this graph, we can see the metal concentration, the aluminum concentration, versus the electrolysis time for the two current densities applied. What we can see is that, as expected, the higher density produced a higher metal concentrations in the coagulants. During the production of the coagulant at the higher current density and at 2 times the minimum contact time applied, it was obtained a metal concentration in the coagulants of 977 milligrams of aluminum per liter in using the brines of Gandia, and 910 average concentration using the brines of nearby Wulpe. In this graph, we can see the energy consumption versus the electrolysis time for the same current densities applied. What we see is that the lower current density applied show a lower energy consumption, but the higher one was used to maximize the metal concentration in the brines. During production, as we can see in this table, Gandia wastewater treatment plant had brines with higher conductivity, so an energy consumption of almost 15 kilowatts per hour per kilogram of aluminum was obtained, while in Wulpen this energy consumption was higher due to the lower conductivity of the brines produced in Wulpen. To guarantee a safe application of the waste-to-coag coagulants in urban wastewater treatment plant, respirometry tests were carried out to evaluate toxicity both on autotrophic and heterotrophic bacteria. This was done using different samples of activated sludge and adding as a concentration of the waste-to-coag coagulant using different type of brines. And what we can see in this table is how the ammonium uptake rate was higher when using the waste-to-coag coagulants with the two type of brines tested, and also the heterotrophic respiration was higher when using this the waste-to-coag coagulant, which means that coagulant didn't inhibit the biological process, and this guarantees a safe application in the system. Also, yard tests were carried out at different aluminum concentrations, targeting phosphate removal. with selecting doses from 5 to 20 milligrams of aluminium to be scaled up during the application in the pilot. The operating conditions during the validation treating urban wastewater in Gandia was to produce the coagulants as mentioned before with the objective to reach the maximum aluminium concentration and in order to have a higher valoration of each volume of brines. The applied current in the electrolytic system was fixed with a higher current density using aluminium electrodes and the higher contact time to maximize aluminium concentration. The electrolyte was a mixture of two brines with conductivity ranging from 30 to 40 millisieverts per centimeter and pH ranging from 5 to 7. You can see in these pictures the prototype installed in Wulpen and in Gandia. The coagulant application was done in Gandia, treating effluent from the first clarifiers of Gandia wastewater treatment plant. The treatment capacity was set at 1 cubic meter per hour, and the coagulant was applied in the biological reactor of the pilot unit that we can see in this picture with a static clarifier. In this table, we show the results at different doses from 0, 5, 10, and 20 milligrams of aluminium per liter, targeting CO2, COD, phosphate, also showing the removal of total phosphorus, suspended solids, and also the turbidity. What we can see in this table is how the optimum dose was fixed at 10 milligrams of aluminium per liter, obtaining around 60% removal of total phosphorus and 76% of COD, with average turbidity removal of 85%. Hence, as a conclusion of this validation in urban wastewater, the brines and metal wastes were correctly valorized to produce the Waste2Coag coagulants. The electrolysis concept was correctly scaled up from previous projects, and the Waste2Coag coagulant was technically feasible to treat urban wastewater in Gandia. Thank you for your attention, and you can follow us in our social channels.
In this presentation, we will focus on the transferability of the technology. That means the results obtained from the generation and dosage of coagulants in an industrial wastewater treatment plant, in particular, Joviar facilities. First, we will introduce the partners involved in this phase of the project. Then we will cover the selection of scraps, metals, and brines, which are the main inputs in our technology. Then we will detail the generation of coagulants using the company brines, and we are going to cover the results obtained using our coagulants in the industrial plant. Finally, we will talk about the conclusions that we reached in this part of the project. As a brief introduction to AIDIMME, we are a research center focused in the metal and wood processing, as well as packaging and related industries. Our mission is to improve the metal, mechanical, and wood sectors in their products and processes. Our services include research and innovation projects, technological services, and laboratory analysis, as well as education through different masters and specialized courses. Our industrial partner in this phase is Joviar, a company based in Alicante, whose main activity is the manufacturing of technical pieces through thermal injection. They also produce molds and carry out electrolytic finishes. And Joviar has more than 60 years of experience in this field, which makes an excellent partner to validate this technology. As the overview of the context, we have three problems to solve. On the one hand, we have the brines, which we have a high generation of brines worldwide, coming mostly from desalination plants due to the scarcity of water. These brines are normally discharged without treatment, which has a negative environmental impact as they increase the salinity of the ecosystems. Then, for the metals, there is a global scarcity of raw materials, which combined to the political instability results in an increase of price of these metals. So it would be very interesting to recover as much as we can, including these scrap metals. And finally, the coagulants. There is a high consumption of coagulants worldwide, used both in urban and industrial wastewater treatment plants. They are normally outsourced and are subject to constant price increases. And both the prices and the demand are expected to increase because of the stringent requirements in the effluent concentrations. So our proposed solution is to valorize these two wastes and transform them into resources as new reagents of the water treatment plants. We do this in the project through electrolysis, which is the way to valorize these two wastes into coagulants. Let's look at the details of our process. Okay, as we mentioned, scrap metals and brines are the main inputs of the plant, but we cannot accept any type of waste. As any other project or process, we need to carefully assess the quality of the metals and brines that go inside the system. First, for the selection of metals, we have to evaluate the quality, it means their composition, to avoid water contamination, the inhibition of the biological treatment, and of course to ensure the good quality of the coagulants produced. We also have to make sure that the shape, the thickness, and the dimensions were compatible in our specific pilot, and of course the price and the availability of those metals. Even though they are scrap metals, they are not for free and they still have a cost. On the other hand, we had to identify the most suitable source of brines for our ELS system. And the brines can come from, for example, from desalination plants or purification systems, in particular from sectors that use high quality water in their processes. The characterization of brines is essential to make sure that they have no pollutants, such as heavy metals, that compromise the quality of the coagulants. We also checked, for example, the conductivity, which is a key parameter, as the power consumption is directly related to this parameter. The higher the conductivity, the lower the energy consumption of the process. Okay, Jovia requires pure water for their high quality processes, so they need to treat their water using a demineralization equipment as the one in this scheme, and which is the one in the picture. The characterization of the brines is essential, as you have known, and this equipment generates several waste streams during its cleaning cycles. That means that we cannot use them directly, but we have to prepare the optimum mixture. What we did is to choose and mix the different streams from the anionic and the cationic column to create an adequate mix for the input of the pilot system. In the end, we were able to use up to the 70% of the streams generated, which also represented a direct saving for the company in waste management costs. The values of the parameters that were measured were within the optimum range defined for the system. So the next step after getting these brines is the generation of coagulants. As you can see in the picture, we introduced the brines from the company in the ELS pilot, the mixtures that we prepared from the demineralization equipment. So we produced both iron and aluminium coagulants. The concentration achieved for iron was around 1,000 and 1,500 ppm, and for aluminium 800 and 1,000 ppm. As you can see in the picture, they have a very characteristic appearance depending on the metal used. This one is iron and this one is aluminium. So with the coagulants produced, we move on to the most important step of this phase, which is testing them in Joviar water treatment plant. That means replacing the conventional coagulants. First, what we did is to define the optimum dosage of the coagulant using jar tests, and then introduce these coagulants into the mixing tank of their plant. As you may know, the surface treatment sector treats waters with a high content in heavy metal, so our goal was to demonstrate that we could effectively remove them from the effluent water, that is, this part of the treatment plant. The results were very good, as we achieved the removal efficiency above 90% for all metals, that means zinc, copper, chromium and nickel. Besides, the treated water met the EPSAR discharge limits, which means that this water was efficiently treated and can be safely released to the sewer. This validation shows that our coagulants perform at least as well as conventional alternatives in a real industrial setting. As the life cycle assessment, we also carried out an initial life cycle assessment to compare the environmental impact of our approach versus the conventional treatment using lime. As an overall comparison, the conventional treatment generates more than 1.4 kilos of carbon dioxide, while the aluminium and iron coagulants produced in the project generate 1.3 and 1.2 respectively, as it can be seen in the graph. If we look to the details in this study, we can see that the main cause of this difference is the production and transport of the conventional coagulant, as well as the sludge generation, which is higher for the conventional coagulants. So finally, to sum up, we performed the characterization of Joviar industrial brines and obtained suitable mixtures for the ELS treatment, allowing the valorization of 70% of the brines on site. We also demonstrated that the coagulants produced are safe and effective for the removal of heavy metals, so the water can be discharged in compliance with the EPSAR regulations. The life cycle assessment confirmed that our approach has a lower environmental impact compared to the conventional coagulants, and overall, this phase of the project has proven that our technology offers an efficient, scalable and robust valorization of metal scraps and industrial brines, turning waste into resources. Thank you very much for your attention.
LIFE Waste2Coag has received funding from the LIFE program of the European Union.